Thanks everybody for joining the SIAM FME online seminar series. And today we have the pleasure of having Francesca Biagini, and I will let Jean-Pierre doing the introduction. He's moderating this talk. And as you all know, Jean-Pierre is like a fundamental figure in the field of financial mathematics, the editor-in-chief of the Society Journal, CFIN, and is also a SIAM fellow. And without further say, I will leave the floor to Jean-Pierre. Please go ahead with the introduction.
Okay, thank you, Agostino. Welcome, everybody. So just to remind you that the talk will be 45 minutes, and then we will have 5 or 10 minutes question and answer at the end. We will keep the question for the end, and you can post them on the chat. If there is a very urgent question, I can ask it to Francesca to answer it. The talk will be recorded and on YouTube SIAM. After the formal 1 hour session, then we will stay on for those who want to gather informally and have a discussion. So after this reminding of the rules, it's my pleasure to welcome Francesca Biagini. Francesca is a professor of mathematics at LMU, Ludwig Maximilian University of Munich. She has a chair of financial and insurance mathematics there. At LMU, she's also the vice president for international affairs and diversity. She's a member of the executive board of the Munich Risk and Insurance Center. Francesca is the current president of the Bachelier Finance Society, with a lot of activities these days. And last but not least, with her family, she's a regular visitor here in Santa Barbara, a co-author and a very good friend. Welcome, Francesca, and without any more delay, the screen is yours.
Thank you very much, Jean-Pierre. I'm moved from your introduction, and to begin, just let me thank the organizers for inviting me. You know, I have been serving for this activity group for 3 years, so I'm very connected to this activity group of SIAM. So it's a pleasure for me. So today I will speak about uncertainty. I think that it was a good topic for these times of great uncertainty and measure risk. So this talk is based on 2 joint work with a former PhD student of mine, Yiling Shang, and a current PhD student of mine, Caterina Baprilla. What is the aim of this talk? So we would like to extend the reduced form setting as formulated by Bielek and Rokowski, now in presence of several priors. So we do not have only one probability measure, but we consider several possibilities for our probability models. So the first challenge will be to extend this intensity-based framework under model uncertainty. And then after this, we will include intensity following an affine process under parameter uncertainty, as defined in the recent work of Fadina, Neufeld, and Schmidt. And last but not least, we will try to introduce the notion of a longevity bond under model uncertainty in an arbitrage-free way. So what should we do for this? The first things that we need to do is to introduce the notion of a sublinear condition operator with respect to a progressively enlarged filtration and the family of probability measures that now are admitted also to be mutually singular to each other. So the concept is that if you have one probability measure, then of course you have a natural, let's say, Prassin operator. If you think about financial mathematics, that is the conditional expectation under this measure with respect to a given filtration. But now you don't have only one probability measure, but you can consider a family of models, of probability models. So this problem has been tackled by several authors. I will present in a second some literature overview, but we will try to extend the definition, the co-structure of Nutzeff and Andel that they have proposed on the canonical space endowed with a natural filtration. So let's start recalling some literature, as I said, concerning credit risk and insurance modeling. There are some papers dealing with modeling uncertainty, but usually the assumption there is that you have a dominated probability family. For example, you can consider the papers of Lien, Schismaier, or Jean Blanc, Matoussi, and Goupillot, and Caponi and Beau. Of course, for financial market, there is been an intensive study of modeling under several priors with different techniques. For example, capacity theory, stochastic control technique. Think about the seminal paper of Denise and Martin, or Sona, Tuzin Shang, and then some more recent paper from Achayo Larson and Sara Biagini, Bouchard, Kardares, Nutz, and of course, all the works of Shigi Peng about the G expectation and co-authors. A pathwise solution that I will present shortly is provided by Nutz and co-authors, or Nutz and Van Handel, Neufeld and Nutz, and other papers that I don't recall it. And this will be, let's say, our starting point. But the point for the construction of Nutz and Van Handel is that it works only on the canonical space, and now with the canonical filtration, with the natural filtration, and the canonical process. And it's not possible to extend this pathwise construction when you consider different kinds of filtrations. Anak Samit, Hu and Obloy have solved this problem for initial enlargement of filtration, when you add to your reference filtration the knowledge of a certain random variable. But of course, if you now consider credit risk or insurance modeling, then you would like to model an event which occurs as a surprise, but still has a F-rate or measurable occurrence intensity. For example, think about the default of an institution, the time of decease of a person. This will be represented mathematically by total inaccessible stopping time with F adapted intensity, where F is your, let's say, starting or filtration, your reference filtration. In this case, it cannot be treated by using the techniques of Nutz and Van Handel, because due to this change of filtration, fundamental properties like the Galmarino test and so on fails. So let's start, however, recalling the natural filtration case, because, as I said, this constitutes the basis for our extension. So we consider a measurable space, omega F, where omega is the space of Cutler function starting from 0, equipped with the metric induced by the score topology, but you can even take the space of continuous functions. And then F will be the Borel sigma algebra on omega, and P omega the set of all probability measures on this measurable space. We consider the canonical process B on this measurable space and denote the raw filtration of B by F. You can imagine F is the reference filtration, maybe you can imagine B as an asset price. And now an important role will be played afterwards by the universally completed filtration F star, which is the raw filtration completed with all sets which have measure null under all measures on this measurable space. So you see already that we are getting technical. Actually, I will try to convey the ideas, not repeating all the technicalities, but of course, these are written on the slides and of course in the papers. So now we select a family P of probability measures on this measurable space, which is, let's say, our model choice. And now the scope is to introduce an alternative concept to the concept of condition expectation under one given prior. And this will be a sublinear condition operator. How can you do this? There are two ways. One is to assume some regularity on the class of random variables, as for example in the case of the G expectation and the works of Shige Peng, or as Nutze van Andel has been doing by assuming some condition of measurability, invariance, and stability under passing of the family P of priors. Why do we need these assumptions? Because the idea is to construct this sublinear operator by gluing together conditional expectations. And since these measures, these priors, may also be mutually singular to each other, it's very difficult to pass together these conditional expectations if you do not have these regularity conditions and assumptions on this set P. Okay, but what is the key ingredient of this construction is the so-called concatenation, which is a pathwise construction. So we take two paths, omega and omega prime, and we call the concatenation of omega and omega prime at tau the path that you obtain by following omega until tau, and after tau you will follow omega prime. And then given a function x on omega, we define the function x tau omega, which is now x evaluated at the concatenation with omega at tau. Okay, and then now more or less we are ready to introduce the F conditional sublinear operator as done in the paper of Nutze van Andel. So suppose now that our model choice, this family of priors P, satisfy this regularity assumption that we have called it assumption A. Then consider a stopping time tau. Then for every upper semi-analytic function x on omega, we can define a function epsilon tau of x, which is defined as the upper expectation or the capacity associated to this P of the expectation under P of x, but now transform it into the function x tau omega, which is actually our initial, let's say, random variable, evaluated at, over the concatenations. I will comment afterwards about this upper semi-analytic function. So this operator is measured with respect to the universally completed filtration, is upper semi-analytic, so it maps upper semi-analytic function into upper semi-analytic functions, and it's actually what we wanted to have. That is, it satisfies this consistency property. Epsilon tau x is equal P almost surely for all priors that we have selected to the essential sup of the conditional expectation under P prime of x given F tau, where P prime are the priors which coincide with P on F tau. So morally, this sublinear operator is the maximal conditional expectation over this set of measure P. In particular, this operator satisfies the tau property. So if sigma is another stopping time, which is smaller than tau, then we have that epsilon at sigma of x is equal to epsilon sigma applied to epsilon tau, as in the case of the standard conditional expectation. And this pathwise for all omega. So this is the construction, it functions very well. Why do we use this concept of upper semi-analytic function? So an upper semi-analytic function is a function such that for all C, the set x greater than C is analytic, that is the image through a Borel measurable function of a Borel set of from a Polish space. So a very complicated definition. Why? Because unfortunately this operator epsilon tau does not map Borel functions into Borel function. So you have to, let's say, weaken this concept. And actually, when it comes to model uncertainty, all assumptions about measurability and later on about integrability plays a key role because by operating through these conditional sublinear operators, you may lose really measurability. Okay, So we have, let's say, rephrase a concept, the conditional expectation, in presence of several priors. And now what can we do in order to introduce a reduced form setting under model uncertainty? So we go another way, and we start by considering gamma, which is a real value that adapt a continuous increasing process, representing our hazard process. In particular, we can also assume that this gamma is generated by certain intensity mu. This is not actually necessary for the construction that I show you, but we will use this later on. So let's assume it. And now, as in the Cox construction of the total inaccessible stopping time, we consider an additional probability space, which is an atomless probability space omega at, with the Borel sigma algebra and the probability measure Piet, and this probability space admits a uniformly distributed random variable Xi. And by using Xi, we define as usually tau tilde as the first t such that gamma t becomes greater or equal than minus the logarithm of Xi. Tau tilde is then automatically a random variable on the product space of omega, the space that I introduced just one moment before, and this omega at. And now on this product space, we consider the filtration G, which is generated by the reference filtration. You can imagine this filtration contains, for example, the information from the financial markets, but also other kind of information concerning the economic condition, the health situation in the world, and so on, and the filtration associated to tau tilde. And then on this protospace, we consider the family of probability measure, which is generated by the product of the priors that we have chosen in the beginning with this P at. Okay. And now what is the key ingredient in our case in order to define a sublinear conditional operator now with respect to this sigma algebra G? It's a very simple result that is also contained in a paper from Caligaro, Jean-Blanc, and Zagari that says that if we have X tilde real valued function, which is measurable with respect to the sigma algebra generated by tau tilde and determinate sigma algebra F, then there exists a unique measurable function phi, which represents X tilde as a function of tau tilde and omega. Okay, so we are fast there. I'm almost there, sorry, I was speaking half in German now. So let me introduce some notation. We denote by epsilon tilde the upper expectation associated to P tilde. And then when I write G of P or G calligraphic P, I mean the sigma algebra or the augmented completed with the null sets, either with respect to a measure P or with respect to all priors which we have chosen. L1 omega tilde will now represent the space of measurable function with finite capacity. And then the expectation that Piet will represent the integration of suitable measurable random variable with respect to the second component omega at. Okay, so now we can actually present the definition of G conditional sublinear operator. So again, we need to assume the condition of Nutzer-van Andel for what concerns the set of priors P, the one that was first defined on the space with the F filtration. And now consider an upper semi-analytic function X tilde on omega tilde, so on this product space, which is an element in L1 omega tilde, or in other words, which has finite capacity. Then the function epsilon tilde t for t given of X tilde, given by epsilon t, this is the F conditional operator, evaluated on phi, where phi is the function determined uniquely X tilde as a function of tau tilde and omega. on the set tau tilde less equal than t, or this function epsilon tilde given by epsilon t evaluated on e to the gamma t, and then the expectation under p hat of x tilde times the indicator function tau tilde greater than t on the set where tau tilde is greater than t, strictly greater, then is a well-defined function. In particular, it's really our desired G-conditional sublinear operator. That means that P tilde does more surely for all these priors in this extended family of measures. This epsilon tilde t of x tilde coincide with the central sup of the condition expectation and the P tilde prime of our random variable x tilde given gt. These P tilde prime are measured such that they coincide with P tilde on the sigma algebra gt. So again, we have introduced an operator which represents morally the maximal conditional expectation with respect to this family of priors. What are the properties of this operator? So first of all, this operator maps again upper semianalytic function into upper semianalytic functions. It doesn't preserve measurability for Borel function either, as in the case of the F conditional operator. Is measured now with respect to G star T. Is of course sublinear in X tilde, but there is a little problem, let's say so, is that the tau up property does not really hold. So we have only a weak dynamic principle condition. That means that for all s less than or equal than t, epsilon tilde s applied to epsilon tilde t is always greater or equal than epsilon tilde s. We can show counterexample where this inequality is actually strict. So why this is the case? So let's do a step back. Here you see I have now including the hypothesis of this theorem that x tilde is L1 in omega tilde. This integrability condition was not present in the results of Nuzzo van Andel because they use a pathwise construction, which is not possible with respect to G. And now the problem is that this epsilon tilde does not map L1 omega tilde into L1 omega tilde. So you're losing not only measurability, but even integrability. And in order to apply twice this operator, you need this integrability because morally you have to exchange conditional expectation with this sublinear operator. And this is not always true. It's true, for example, is the so-called Young's commutability principle also in other situations. So this is, for example, one main difference with respect to our approach with respect to the canonical space situation. Okay, but actually we were hoping that to recover the same properties as a conditional expectation in the standard case, so that we can use this sublinear operator as a pricing operator. But there are still good news in the sense that consider now the typical form of a life insurance liabilities. So represented by a random variable x tilde, which gives you, let's say, a payment y if tau tilde is greater than capital T. Let's say if the default has not happened before time of maturity, or it provides you with a recovery payment set at time tau tilde if a default occurs before or at time of maturity. Then under some actually a long list of technical conditions of the process set and y, and the function y, we have that actually if I apply now the G sublinear condition operator to x tilde, then this will map L1 omega tilde into L1 omega tilde, so we will preserve integrability and the tower project will hold. So for all application in for insurance modeling or the credit risk and the model uncertainty, this is our candidate for pricing operator, and he has the required property for this. I will use this now in two directions. First of all, the first question that I want to address is, okay, consider now that I have a payment if Y, so an annuity if the default or the decease of a person has not yet happened. Now we have that this equality, so the epsilon tilde applied to this random variable as the indicator function actually coincide on the set where tau tilde is greater than small t with the F condition operator. And now you see, you obtain a form that you may recognize, and because here you have now the intensity. So the first question that I will address will be, can we compute or can we imagine some frameworks and the model uncertainty under which we can compute this, as it would be the case if I would have a condition expectation instead of this operator, and here an affine process in the classical sense. And then afterwards, we will use these results in order to provide a definition of longevity bond and the model uncertainty. So before we can address the question if we can compute this object here below, I hope that you can see my cursor. I need to introduce quickly the results of Fadina, Neufeld, and Schmidt concerning affine processes under parameter uncertainty. So now we consider this set, PAC's SIAM, which is actually the family of all semi-martingale laws for the canonical process, such that the canonical process has almost absolutely continuous characteristics. Given so in terms of some integrals of predictable process beta, B, and alpha. Now fix a compact set theta, which is the product of intervals, and consider the set value functions B star x and A star x. For each given x, this function actually are take values in interval, okay? Where you can see that the extremes of this interval are fine functions in x. So now we can give the definition. We say that a semi-martingale law for our canonical process, given the set theta that I just introduced with associate S star and B star, is said to be affine dominated on the interval T capital T by theta if the semi-martingale characteristics satisfy that beta P belongs to beta star beta Bs and alpha S belongs to alpha star B, dP dt for almost all omega S in omega times T, the interval small t capital T. So what does this mean? Let's take a step back. It means now that the semi-martingale characteristics, or at least the integral generating the semi-martingale characteristics of this semi-martingale of the canonical process are actually allowed to vary into an interval whose extremes depend on the canonical process and are fine functions of the canonical process. Now, if beta or alpha takes a value on one extreme of this interval, then you have again the standard affine case. So now you understand why we have been talking about affine processes under parameter uncertainty. So let's, in particular, to refine this definition, we say that a family of semi-martingale laws such that the canonical process starts in X with probability 1, and P is affine dominated on the interval T capital T by theta, is called affine process, and the parameter uncertainty started at X in T and denoted by ATX theta. For T equals 0, then we will drop the T and write simply AX theta. Okay, how can we use these notions in our setting? So we now consider a canonical process with two components, beta S, beta mu. One, why? Because we would like now to introduce actually a financial market model under several priors. And this financial market model consists of a risk-free asset S0, which we put equal 1, so we eliminate this from the beginning, and the risky asset S, which is now assumed to be driven by the first component of the canonical process. And then we will have an F predictable intensity mu, which is now given or identified for the sake of simplicity with the second component of the canonical process, and let's assume also this to be non-negative. But here you can actually consider much more general setting, okay? And now we would like to consider some families of priors in order to have uncertainty on the asset price. For example, you can think that the volatility of this asset price is uncertain in the sense that it can vary in between two given bounds, but you don't know it. You know the law of it actually, like in the G expectation case. But also we would like to have this affine structure and the parameter uncertainty for the mortality intensity. So for every T and omega, let's consider the family of probability measured set T omega, which is given by the measure which belongs both to P, the initial set of priors, which we have identified in the first part of this course, and also to this set AUT omega UT theta, which is actually the family of all measured P mu, which are semi-martingale laws for our canonical process, or second component of the canonical process beta mu for our mortality intensity, for example, and are also affine dominated on the interval T capital T by theta. So, as I said, we wish to consider these two properties for the families of probability measure that we are now going to use. And the aim is to use this family of probability measures in order to define on it our G conditional Sabline operator. Okay, the construction that I've shown can be done for all family of prior satisfying the hypothesis of Lutz and van Andel. In particular, let me assume some further condition on P. We wish to have that under all priors in this initial family P, the process S, which represents our risky asset, is a local martingale with respect to F. So that under each P, the corresponding market model is arbitrage free. And now the question is, does this family set T omega for all T omega satisfy the hypothesis of Lutz and van Andel that we have called it assumption A, so that we can define this G's conditional Sabline operator? And the answer is yes. So we can have both the structure on the market, the financial market model, as well this, let's say, non-linear affine structure for the mortality intensity. Okay, so this allows us to generalize a result of Fadina, Neufeld, and Schmidt in dynamic sense. So the family set 0 omega, so where T is equal to 0 for simplicity. And now consider this case. Suppose that there exists an element, a prior P bar in this set, and a P bar F prior motion W such that, let's say, our mortality intensity to simplify, under Piet is given by the unique strong solution of this equation. You see, the SIAM model. Then we have that P bar are more surely the F conditional operator applied to the expectation of minus the integral between small t and capital T of the mortality intensity in the S is actually an affine structure. So it's given by the exponential of the function phi plus psi times beta mu t, where phi and psi are deterministic functions solving these Riccati equations. So this already gives us a first answer to our question that was, I come back, sorry, it's always a bit annoying when one goes back with the slides, but I wanted to recall you the problem. The problem was, can I compute this right-hand side term here? So can I generate, in a certain sense, a affine structure under model uncertainty, and this will allow also us to compute the G conditional operator. And the answer is yes, by using this extension of these results that I have presented now. Okay, but now we want to take a step further and use this setting, this framework, to introduce the notion of a longevity bond. So now we need to consider the product space, omega tilde, and the filtration G, that is both the filtration generated by the reference filtration and the filtration of our stopping time, tau tilde, and for every t omega, we consider the extended family of probability measured Z tilde, which is generated by, again, by the product of the elements P in ZT omega and Piet. Piet was this additional, did measure on this additional probability space within the Cox construction of tau tilde. Okay. So in this market model, under several priors, we wish to introduce the notion of a longevity bond. In order to do this, we follow the approach of Cairns, Blake, and Dow, and define a longevity bond by means of a survival index. So a longevity bond with maturity capital T is now a bond paying the survival index, Y, at time capital T. And the survival index is now defined as the exponential of minus the integral of the mortality intensity or minus the hazard process. This is the definition given by Cairns in his work. And of course, now if you would be in a standard financial market model, then you would take, let's say, the pricing measure from the financial market. This could raise a big discussion, but let's say we have one, and then price this bond by taking the conditional expectation under the given pricing measure of Y. And doing this, you add an asset to the market in an arbitrage-free way. The problem is now we do not have this pricing measure. So how can we define or associate to this longevity bond a price process such that the resulting extended market is arbitrage-free? In order to solve this problem, we need, first of all, to have an idea what is the possible or tentative candidate price process. And of course, we, let's say, intuitively choose the G conditional operator, epsilon tilde, and define the price process associated with the longevity bond as epsilon tilde at time t of the survival index at time capital T. And this, of course, intuitively corresponds to choose the maximal price among all possible models, as given by this theorem that we have proved with Yiling Shang. So yeah, I need to make a technical observation, but if you don't care, it's also fine. And that this operator epsilon tilde t is not always card-like. So this definition, if you really want that your price process is card-like, then you have to take a modification of this definition that we have in the paper. In the paper also we illustrate several cases where this operator is always card-like, for example, in the case of the G-random expectations. From now on, for the sake of simplicity, I assume that epsilon tilde is card-like. Okay, so just to avoid technicalities. And now we use the concept of absence of arbitrage of the first kind and the model uncertainty as introduced in a paper by Sara Biagini, Bouchard, Cardaras, and Nutz. We consider from now on strategies which are simple. That means that are constant over in some intervals of time. So here HS will represent investment in S, and HY will represent investment for the longevity bond. This is not a very restrictive assumption if you think about insurance companies, which are compelled to actually to keep fix the portfolio over quite long interval of times. For example, in Germany, 2 weeks. So they are allowed to reshuffle the portfolio every second week. And now, of course, we need some admissibility conditions on these strategies. So we assume that these simple strategies generate wealth processes given by this expression, which are, let's say, bounded from below, Z tilde quite surely. And now, what is the definition of no arbitrage of first kind? In order to introduce it, I need to recall the definition of super hedging price of a given claim F in this framework. So this will be given by the smallest amount of capital, initial value of a simple admissible strategy whose terminal value super replicates the given contingent claim, zeta tilde quasi surely. And now we will say that a market model on omega tilde x present no arbitrage of first kind with respect to zeta tilde if for all s in the interval 0 capital T and contingent claim f, which is zeta tilde quasi surely finite and GS measurable, a super hedging price equal 0 implies that f is equal 0 zeta tilde quasi surely. So, of course, you can characterize this no arbitrage of first kind also for each p tilde if S has continuous path, otherwise we have that only one direction alt. But let's try to conclude and focus on the pricing, on the introduction of this longevity bond. So if now we have that for every wealth, for every portfolio value associated to a simple admissible strategy, we have that for each p tilde and zeta tilde and each t in the interval 0t, we have that the expectation under p tilde of the portfolio value at time t is less or equal the expectation under p tilde of the portfolio value at time 0, then the extended market model satisfy the no arbitrage condition first kind. So our extended market model is arbitrage free under model uncertainty. You will maybe be surprised by such condition, but this is actually easy to be explained. And here we list so some properties that implies this condition. For example, it's easy to understand that as soon as this portfolios are super martingales for all P tilde and zeta tilde, then of course this condition is satisfied, and it also satisfied, for example, if you have the asset price is always represented by non-negative process zeta tilde quasi surely, of course, for all these family priors in this family. And if we do not allow short selling, both in the risk asset as well in the bond. This is again actually a natural constraint for insurance companies. Of course, this could be a bit more critical in credit risk modeling. However, of course, as soon as we consider model uncertainty, we need a trade-off in between further conditions and our results. So with this, I would like to conclude, and thank you very much for your attention.
Thank you very much, Francesca. Very interesting talk. I see that we have one question from Arash. So Arash, you can unmute yourself.
Hello, can you hear me? Hi.
Yep.
I probably missed that part. Can you please explain your admissibility condition for the portfolio and how it is related to the classical admissibility for the portfolios when they are bounded from below by some constant?
Yeah, sorry, because I was maybe a bit quick in the end. I couldn't see the time. Where I read, yeah. So now do you see this? My slide number 32. So here actually this H simple is the family of all simple predictable processes, simple strategies, whose value is always non-negative, but you can assume.
Oh, okay. Okay, non-negative. So the bound is without loss of generality, you took the bound to be 0.
Exactly.
Okay.
You can always, since they start from a value X, you can always say bounded from below.
I also have another question, not related. If Jean-Pierre let me to ask that question too.
Go.
Okay.
Go.
So I would like to know exactly. I didn't get that part that you said that if we work on the canonical filtration, we would not achieve the cross structure between, for example, the a Brownian motion and a different Brownian motion or different survival rate. Or maybe I completely misunderstood that part.
No, I was meaning something different. That is deconstruction. So I come back. I hope that you can see this. The problem is that I had to skip it actually. But there is this construction. Sorry. So we have this. This simply related to the construction of Nutze van Andel of the sublinear operator. That is, they define this concatenation. Then they define this, let's say, extended function on the concatenation. But the idea behind is to have that for every probability measure P, they define this measure P tau omega. Okay. And they prove that this is defined as they define this as the F conditional probability measure P omega tau. And this is construction is only possible on the canonical space. You cannot mixture.
So your way out is to make a space of the cross of two spaces. Exactly. One canonical filtration, then the other one is a different filtration, an arbitrary filtration.
Exactly.
Okay, thank you so much.
Okay, so we have another question from Agostino. So Agostino.
Thank you, Francesca. So just wanted to clarify, in the credit risk application that you mentioned, like the longevity bonds, do I understand correctly that if a default intensity exists for a specific firm, it's allowed to depend also on the past default events? So you could basically make default intensity depending on which other firms defaulted and at what time this happened. Or I misunderstood.
Not really in the approach of in this approach.
I see.
Not in this approach, because it's only so that it's what you allow, you simply consider here, I have to come back, is that these semi-mapping characteristics are uncertainty, so they may take their processes, and you only know that they are included on these bounds, which depend on the canonical process.
I see.
But you don't have other defaults or other, maybe you can extend it,
I see.
but you don't, at this stage you don't have it.
Okay, interesting. So it's good. Somebody can build on it and add.
I have an idea how you can do this. And this is for me now. So instead of considering that this, you could do like this, that you consider maybe instead of having that, you can consider d-dimensional intensity, so connected to the different taus, and then you simply allow that this dimensional process varies into a, I have to compute the dimension, a certain, let's say, cube.
I see. So it depends on the group, on a group of.
Yeah, I mean that the bound is not an interval, but again a d-dimensional setting.
I see.
Or a product, and then you could cross them.
I see. So you could enlarge with this additional information.
Yes, I think so.
Interesting.
So, thank you. There is a follow-up question from Monique. So Monique, you can unmute yourself and.
I lose that, but it's not a question. It's just a remark about the previous question. If you have several defaults and you would like that the intensity depends on the past default.
Yeah.
So it will be quite easy if the defaults are ordered. If the defaults are not ordered, you have to work with successive enlargement of filtration, and it can be really difficult.
Sincerely, I mean, if you really want to have so one is the affine structure. That was my answer concerning how to extend the affine structure. The other is really, as you were saying, multiple defaults. I think technically it's difficult to define this sublinear condition operator.
Yeah.
Because you lose every time measurability, integrability. It's really a mess. So one would have to think. So the way would be maybe the one illustrated by Monique, to have ordered, but I have no really idea how to do this now, technically.
It can be very difficult.
Maybe another route.
Especially if there are more than 100 defaults, it's just a nightmare.
Yeah.
Maybe another route will be to bring back these infamous copulas.
Ah, yes.
on the Xi function.
But you need a dynamic copula. The copula which moves with
uncertainty, with copula with uncertainty.
So I guess it would be also really helpful.
What do you mean, Jean-Pierre? Infamous? No.
No, we will discuss that after we stop recording. Any other serious questions? Nobody?
Igor, I think, has a question.
Igor, yeah.
So I have a quick technical question. So you had this, actually, you have now the right slide that I want to ask. So you had this weak form of strong time consistency, which is not the tower property. And then somehow it became equality. It became strong time consistency, which you need for pricing, obviously. So how would that happen? Can you give some intuition what is behind that?
Yes, I mean, because in order to have this equality, you have to exchange the order of integration morally. Okay, and with this structure, and with this hypothesis, you see, I have very strong integrability hypothesis that I didn't comment. There it works.
I see. Now I see. Okay.
So do I understand correctly that when it doesn't work, it means that the expectation is infinite?
No, not really. can be finite, but you cannot use Fubini-Tonelli. I mean,
Okay.
Because maybe it's not measurable anymore in the sense that you need.
I mean, it is. You lose measurability with all of these things. So that's why you have this upper semi-analytic and stuff.
Yeah.
I understand. Thank you, Francesca.
No, it's a very, very fine point. Actually, a perfect example to show the students in order to let them understand why measurability is important. Because you never see this actually in this. And then there is this important lemma from Jan that actually was a suggestion of Shige Peng. And there are some sufficient conditions. In the end, you need some upper order of condition expectation and so on morally. But
Okay. Thank you. So I guess if we have no more question, last call.
I stop sharing my screen. So maybe.
Yeah, maybe. Okay. So if we don't have any other question, thank you again, Francesca, for a very interesting talk and a lot of questions. And then we will go to the second part of the meeting, the informal gathering, after we stop recording.